All right, so all of chapter 10 is all about counting methods. 10.2 focuses on that shortcut we were beginning to learn for how to count, how to find out how many results you're going to get. Okay, and that's sometimes pretty handy. All right, so what I have on the front page of this is what you just did on that 10.1, 10.2 handout. Okay, so we're going to learn how we can count up how many, and we're going to find that there's a shortcut that we can use if we have a uniform tree diagram. So like when we did that first tree diagram where we did possible results when 3 fair coins are tossed, we actually can see all the possible outcomes. So we could actually have written them. I want that to be blue. Okay. And there would have been 8 of them. And I could have used my tree diagram to help me see what they were. And then I can count and see that there are 8 possibilities, right? 8 different ones. Okay. Now, this particular tree diagram is uniform because, okay, there were 2 possibilities for the first toss, and then for the second toss, there were 2 branches off of each. Now, the fact there's 2 branches here and here is what matters. It doesn't matter whether you have the same number of branches for the first toss, but we just happen to have the same. So the way to think about it is I'm tossing, I have 3 tasks, and I'm tossing the coin each time, and I have 2 possibilities for the first coin times 2 possibilities for the second coin times 2 for the third, and that's a shortcut we can use to get how many. But the reason we can do that shortcut is because the number of branches, number of possibilities for a particular thing is the same, okay? And so here, the number of possibilities for each of those was 2 each time. And so it turned out to be 8 possibilities. Okay? Now, that means you had a uniform, that's important, a uniform tree diagram, where on this one, there were 2 branches here, okay? But then here you only had 1 branch, here you had 2. See that? Here you had 2 branches, here you only had 1, here you had 2. So since when I go to make my second toss, which is right here, on one of them I only have 1 possibility, on the other I have 2 possibilities. Can't use the shortcut. So I can't use the shortcut. Because the tree diagram is not uniform. Okay, I would have to actually know, I could make a list of how many I get, all the different results, and just count them, but I can't use a shortcut to get how many. So I'm looking at the tree diagram while I'm listing this. We did it earlier, but I just want to be complete. Okay. And then finally T, 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 T. Really it's 1, 2, 3, 4, 5, 6, 7, 8 different results. Okay, 8 possible results. Okay, but I can't determine them by using the shortcut. Okay, now the name for this shortcut is called the Fundamental Counting Principle, sometimes abbreviated FCP. It sounds complicated, but it's just saying what we've already done. Okay? So when a task consists of maybe different parts, like maybe you're going to roll a die and then toss a coin. Okay? So if the first task can be done in a certain number of ways, the second task can be done in a certain number of ways, and so on. So if you have a uniform tree diagram, then you're going to be able to use this shortcut. So like if we tossed a coin and then, let me do roll a die first. If we rolled a die and then followed that up with tossing a coin, okay, that would be a uniform tree diagram because we'd have 6 possibilities here, 5, 6, and then there would be 2 off each of those branches, right? So it would be uniform, and what we could do, if we just needed how many results there would be, is we could see there's 6 outcomes when you roll a die and 2 outcomes when you toss a coin. So I'm going to get 12 results. Okay. All right, so looking back at those 2 tree diagrams for that first case versus the second case. With the first case, that was uniform. Okay, you were tossing a coin 3 times. So you had 2 possibilities for the first coin, 2 for the second, 2 for the third, and that gave us 8 possibilities. But when you did the second one, that was not uniform on the previous page. That was not uniform. So you can't use the fundamental counting principle. You'd have to do something else. All right, so let's look at this situation here. So on this problem, we're trying to count the number of odd 2-digit numbers we can make without repeated digits in them. Okay, so if we just initially try to set that up, what we might be thinking is this. We might just be kind of exploring it a little bit. So your digits, all the digits you could have are 1 through 9. Okay, those are the 10 possible digits. Okay, and you might be thinking about, okay, so I'm trying to create these numbers. All right, so when I go to do that, you might be thinking about, trying to create a number like 63, right? Picking your first number, you might be thinking of the tens. And if I was thinking about the tens, my options for the tens place would be a 1, a 2, a 3. I couldn't start with a 0. Okay. Okay. A 7, an 8, or a 9. Okay. Now I want you just to kind of think about this. So I'm thinking about picking my tens place first. Then when I go to pick what's going to happen in the 1 spot, I want these numbers to be odd. So that means that they have to end with an odd number. And I'm not allowed to repeat digits. So like if this were a 1, then it could only be followed up by a 3, a 5, a 7, or a 9. But then if I started out with a 2, I could actually have the next digit be a 1, couldn't I? So it could be a 1, 3, 5, 7, or 9. So do you see all the way down this tree diagram, if the number were odd to start with in the tens spot, then I'd only have 4 options in the ones place because I wouldn't be able to use that odd number in the ones place. But if my numbers were even, like the 2, the 4, the 6, or the 8, I'd be able to have 5 possibilities for what's in the ones place. And if I do that, the fact there's 4 branches here and 5 branches on this one, 5 branches on all the even numbers, that would mean this technically wouldn't be a uniform tree diagram. Technically not really uniform. Okay? But what I could do is I could think that if in the tens place I had an odd number, okay, then in the ones place I would have 4 options. So if I have an odd number in the tens place, okay, then that means there would have been 5 options for the tens place. So that's the tens. So if I have an odd number in the tens place, there would be 5 options in the tens place, but then just 4 options for the ones place, because I need the ones place to also have an odd, but I've already used it up, okay? So I have 5 options for what could be in the tens place and 4 options for what could be in the ones place. So all of the numbers that start with an odd number in the tens place would have 4 branches after it, which means I would have 20 different numbers that would be odd followed by odd. They would be things like 13, 15, 17, 19, 21, 23, that type of thing, okay? And I'm just not finishing the rest of the tree diagram. Okay, then what if I made my tens place even? If my tens place is even, I can't use a 0 because in the tens place, that would mean that the number's not 2 digits. Then if I used an even in the tens place, then there's only 4 options in the tens spot. But then since the first number was even, there would be 5 options in the ones place. Okay, so that would wind up giving me another 20 possibilities, and they would be things like 21, 23, 25, 27, 29, and I'd have 5 there, I'd have another 5 following that, another 5, another 5. So even though the whole diagram wasn't uniform, I could have broken it up into 2 cases, the case where the tens place was odd versus it being even. Okay. Another thing I could have done is just pick the ones place first. The ones place has to be either a 1, a 3, a 5, a 7, or a 9 if I want an odd number. Now I could go back and pick my tens place. And so in the tens place, I can't start the number with a 0, but I could start it with any of the other numbers, except I can't repeat a 1. So this one would be 2, 3, all the way down to 9. Okay, this one could be, can't be a 0 because I can't start with a 0, but it could be a 1, a 2, can't be a 3, but it could be a 4, all the way down to a 9. So when you think about that, you had a number that you used here already that you can't have over here for the tens place, and you can't have a 0 in the tens place. So it can't be this number, whatever this number is to start with, can't be over here, right? And you also can't have a 0. So that means there's going to be 8 branches each time on these. Okay? If I set it up, there'd be 8 branches each time. So there were 5 possibilities for the ones place, and then there were 8 possibilities for the tens place, and that would give me 40 possibilities. So we could have designed it to be uniform. This one would have been uniform, where this one technically isn't really uniform, but we could separate it and consider 2 cases. The cases where you started with an odd number, and then the case where you started with an even number.